Hi everybody, welcome back to another episode of Engsci Recap. My name is Jason. I just finished my second year of engineering science at U of T, and today I'll be talking about the course ESC 195 Calculus 2. So ESC 195 was a course I took in my winter term in first year, and I had Professor Jim Davis. So the main course topics I went over include basic calculus 2 things, excuse me, like L'Hopital's rule, integration techniques like trig sub, partial fractions, etc. Also applications of calculus, so arc length, surface area of revolution. We learned about parametric curves, polar coordinates, sequences and series, which includes convergence tests, Taylor, Maclaurin, binomial, and Fourier series, as well as vector functions, multivariable calculus. So we learned about the gradient vector and the directional derivative, Lagrange multipliers, which I'll talk about today. So today I'll talk about one of the questions from the final exam I wrote on April 28th, 2021. It was question 8, and it pretty much covered one thing and one thing only, and that was Lagrange multipliers. And the reason I decided to cover this question in particular is Lagrange multipliers feels like one of the most sort of unique concepts that was taught in this course. And I didn't want to cover just like a random integration question. I feel like the Lagrange multipliers seems like it would be very useful in practical applications, and so yeah, I just felt like it would be the most useful to sort of remember, I guess. But there are a lot of useful things to remember in this course, so it was hard to pick one thing only. But this is the question, and it's very simple. Basically, find the maximum and minimum values of a function f constrained to the sphere x squared plus y squared plus z squared equals 1. And we need to use the Lagrange multipliers. So I'm going to cover exactly what Lagrange multipliers is, or the method and the theory behind it. So basically, we can use Lagrange multipliers when we want to find the maximum and minimum values of a scalar function f subject to a constraint g equals k, where g is a function and k is a scalar. So first of all, we should notice that f equals c and g equals k are level surfaces. Um, I'm not sure if level surfaces applies for n dimensions, but I'm going to assume it does. And we also need to notice that the level surfaces must intersect at a single point if c is a local minimum or maximum value of f. Now the reason this is because if they intersected at multiple points or infinite points, then c would not be a local maximum or minimum value, because we could increase it or decrease it to get an even larger or smaller value, while there is still an intersection, and it's only at the point where they have one point of intersection that it is a local optimum. So we should also notice that the intersection at a single point means the two surfaces share a common tangent plane, which means that their gradient vectors are parallel, since the gradient vector will be normal to that surface. So suppose we define h of t is equal to f of r of t, where r of t is a curve, a parametric curve, on the level surface defined by g equals k. So we can use r of t naught to represent the coordinates of an extreme value of f. And if we take the derivative of h, we'll see that h prime of t naught should be equal to 0. And that's because, it's an extreme value. So the derivative should be equal to 0. And using the chain rule, we see that the gradient of f dotted with r prime of t naught should also be equal to 0. However, we know that the gradient of g dotted with r prime of t naught is equal to 0 is also true for every curve r of t, because r of t is just a parametric curve that exists on the level surface, and the gradient of g will be normal to that level surface. So this is also true. And from this, we see that the gradient of f and the gradient of g are parallel. And this explanation you can find in Calculus 8th edition by James Stewart. And this is essentially the method we use to solve for the maximum and minimum values. So this is a restatement of the problem, but basically, in order to set up our system of equations to solve for x, y, z, we say that because the gradient of f and the gradient of g are parallel, we can set them equal to each other, but multiplied by a constant lambda. And so now you're probably wondering, okay, like we have n spatial variables. Okay, let's say we're in 3 dimensions, so we have 3 spatial variables, and then we have lambda, which is unknown. But we only have 3 equations from setting the gradients to be parallel. So the final equation we need to complete this system is going to be the constraint that, well, we're subjected to, which is that g is equal to k. So now you should see that in n dimensions, we would have n plus 1 equations and n plus 1 unknowns, because we have n dimensional unknowns and then one additional unknown, which is the factor lambda. So now we have n plus 1 equations for n plus 1 unknowns, and we can solve. Then we want to find all the local optima, and we want to evaluate f at those optima to find the true maximum and true minimum on this surface. And again, this is from James Stewart, Calculus 8th edition. So now let's go back to our problem and set it up. So we're given f to be xz plus y squared, and we're subjecting it to the constraint g is equal to 1, where g is equal to x squared plus y squared plus z squared. So obviously the first step will be to take the gradient of both of these functions. And we see they're relatively simple. Now we can set up our system of equations by using an arbitrary constant lambda to show that the vectors are indeed parallel. And the final equation will be the constraint equation. So I'm just going to label these equations 1 through 4. We should notice immediately that if we want to satisfy equation 4, lambda cannot be equal to 0. Because if lambda is 0, then x, y, and z are all 0, and then we're no longer on the sphere. So if we should notice that equations 1 and 3 relate x and z, so we can substitute equation 3 into equation 1. And we get that z is equal to 4 lambda squared z. So there are a couple cases to consider here. The first case we can consider is z is equal to 0, and the second case is lambda is equal to plus or minus 1/2. For equation 2, since lambda is not equal to 0, there are 2 cases to consider. So case 3 would be lambda is equal to 1. That would just give us 2y is equal to 2y. And then case 4 would be that y is equal to 0. So we have 4 cases to consider. Let's go with case 1 first. So if z is equal to 0, that would give us x is equal to 0, which gives us y squared is equal to 1 by equation 4. And that means y is equal to plus or minus 1, but we actually don't care about the sign because in our expression for f, we just have y squared, which would give us 1. In case 2, which is lambda is equal to plus or minus 1/2, plugging that into equation 2, we would see that y has to be equal to 0. We also should notice that in this case, equations 1 and 3 tell us that x squared is equal to z squared. And so plugging this into equation 4, we would get 2x squared is equal to 1. So x is plus or minus 1 over square root 2. And again, we have 2 cases to consider. The first one is that x is equal to z, in which case f would evaluate to 1/2. So if x and z have the same sign, we would see f is equal to 1/2. In the case where they have opposite signs, so that would be lambda is equal to minus 1/2, we would see that f would switch signs as well. In the third case, we consider lambda is equal to 1. So using equations 1 and 3, we would know that x and z must be equal to 0. And in case 1, we already covered the case where z is equal to 0. So we actually don't need to even consider this anymore because this is redundant. We've already done this. And in case 4, we set y is equal to 0. We show that z is equal to 4 lambda squared z. And we again get two cases, z is equal to 0 and lambda is equal to plus or minus 1/2. But we've covered both of these cases already. Those were case 1 and case 2. So this is redundant. So therefore, we have these optima to consider. We have 1, 1/2, and minus 1/2. So therefore, we can conclude that the maximum value of f on the constraint surface is 1, and that the minimum value is minus 1/2. And that's it. So before I end off this video, I'd like to make some quick acknowledgements. I'd like to thank Professor Davis for the course and the final exam content, and I'd also like to thank my tutorial TAs, Amzel, Jeffrey, and Alex, as well as the individuals who I took this template from. But yeah, I hope you enjoyed, and I'll see you in the next video. Thanks so much.